Middle East Technical University, Ankara, Turkey. I'm here as a visiting professor, and while I'm here, I was asked to make a colloquium talk. So this is that talk, and we are going to talk about hypothesis testing and parametric statistics in education. Thank you for coming to the session and just listening to whatever I'm going to present. So this is not going to be an in-depth explanation of how analyses are going to be conducted, but this is more like clarification and organization about statistical analysis and statistical tools and how and when they are used in educational research. So this will be like, as I said, like a clarification, like a summarization, like organization of information. I hope everybody is able to see the slides. Could you please, all of you, type in into the chat area hello or hi or some kind of greeting so that I can understand that I'm not talking to myself. You can say it here. It's could you please type in into the chat area hi, hello, something, so that I know that you are there and you are with me. Oh, someone is listening very carefully. Maimuna Ikram, thank you. Rafitza, hello, thank you. Wang, thank you. Thank you so much. Chao Yu Mei, thank you. Thanks, everybody. So let's start with the talk. I hope it will be fruitful for you, and you can have some kind of a better insight of what we are doing in statistical analysis when we are conducting a statistical analysis for educational research. So, you know, educational research is a behavioral research. So what is the characteristics of a behavioral research? This is a behavioral science field. What do we understand from behavioral? Behavioral means things are happening in the mind, but you can't just open the mind and look inside and see, oh, this is red, they have learned it, or this is red, they don't like it. This is blue, so they are highly motivated. We can't do such a thing. We have to look at the behavior to understand and interpret what's going on in the human being, including the learning. So the goal of the behavioral research is to understand the laws of nature that apply to the behaviors of living organisms. Since we can't directly look inside the mind physically, we have to interpret the behavior of the livings so that we can have an understanding of why and when and how they will act like this. But we need to measure them. So how are we going to measure? We can measure how many times somebody is laughing when there is a there's some kind of a joke. We can measure the face movements. We can measure the body movements. We can also measure their feelings. How can we measure them? We can use psychometric measures for measuring their psychological behaviors. Here's a cartoon for that. The way I feel is hard to quantify. So, and we are trying to measure that. How hard on a scale of 1 to 10? So we are measuring how hard that feeling is. This might be a very basic question, but we have to ask that to settle down our travel through what we are doing for educational research. So what is statistics? Why are we using statistics? Hi, welcome. So you can ask for, when I ask questions, you are more than welcome to answer it through the chat, okay? So if you would like to provide answers, I would be happy. And those who are here, they can just say it out loud whenever they have a question or whenever they want to express their opinions. So what is statistics? Statistics is a science, and it is about collecting data, organizing and describing it, and drawing conclusions from it. So this is what we try to do. We want to have chunks of information, which we call data. What could those chunks be? For example, the participants' age, the participants' departments, the participants' field of study, the participants' marital status, the participants' gender. All of these particular things are actually data, but when we turn it into a meaningful information, when we bring them together, synthesize them, and turn them into a meaningful information, that's what we use statistics for. So we are using the particular data to have meaningful information. We can summarize to which group a specific talk is of interest and why that group is interested in that type of talk. And the statistics the statistical methods have to have these states. It is about collecting data, and for that we have to have a sample. We need to have surveys, observations, simulations, and so on. And we have to organize data. What kind of data is this? Is this a data that is a measurement? Is this a data that reflects an opinion? Is this a data that cannot be compared to anything else but is unique, like the choice of a car, the choice of a drink, the brand of a shoe that people buy? This could be all characterizing data. And there, as you might remember, there are 4 types of data. Does anyone remember the 4 types of data? No one? I'm going to tell the first one. Ratio is one type of data. Okay, numeric data, they are all numeric, but what else? or yes, in ratio, interval, that's correct, nominal, and ordinal. We have the answer. Thank you, Sarah and Ömer. We have 4 types of data: ratio, interval, nominal, ordinal. Ratio data is actually a quantified data which has true zero. Interval data is also a continuous data without a true zero. And nominal data is like the brand names that people prefer. It's the brand name. And ordinal is like when you put them in an order, like most like, less like, for example, a Likert scale of data, okay? And we have to characterize the data, we have to present the data, we can use tables, charts, statements, interpreting results, okay? And then we have to just interpret the results if it's a descriptive data. Okay. Need to put this somewhere. Okay, is it okay? So this is what statistics is doing. This one low. This is what statistics is doing. Statistics is the way to get information from data. So we have the data like facts, especially numerical facts, collected together for reference or information. We use the statistics so that we can turn it into information, which is knowledge communicated concerning some particular facts. We are trying to find the facts about a specific procedure, concept, whatever it is. The steps in statistical analysis in education are as follows. From which fields are you? Can you tell me from which field everybody is? Science education. Educational technology. Educational technology. Vocational technology and education. Okay, educational technology. So you are from all faculty of education, which means your steps in statistical analysis will be very similar. In statistical analysis, different from natural sciences, when we do want to do a research, the starting point is, what is the starting point? Where do we start in an educational research? For doing research, what is the first step that we do different from natural sciences? No, that's not the first step. Instrument is far later. Thank you. So we had to identify this problem. First, the problem statement. Why is it different from natural sciences? Because in natural sciences, you don't have to start from a problem statement. You can just start from curiosity, whether something is related to something else. But in educational research, generally, the first step is to state the problem. What are you interested in? And why? And what is the problem with that? The second stage is stating your research question. So you you turn that problem statement into a research question that can be answered by means of statistical analysis, whether a mean is different from another mean, whether a mean is different from a population's mean. Those are typically asked research questions. So then we have the statistical questions. Statistical questions include comparison, mean comparisons, or sometimes even predictions. And then you collect the data through the data collection process, and then you end up with statistical conclusion. The statistical conclusion, if you have set the hypothesis, if you are doing a hypothesis testing, can have only two results. Can have only two results, and they are mutually exclusive. First of the results is your hypothesis was true, you accept the hypothesis, or you reject the hypothesis. Can't be anything else. In the statistical analysis, in a hypothesis testing, it cannot be a maybe or sometimes, okay? You have to come up with a clear result, either accept or reject the hypothesis. And you can have two types of hypotheses which are also mutually exclusive. One, you can have the null hypothesis, which says, no, there is no difference, they are not different, there has not been any change. Or the second one, the alternative hypothesis will say there is a difference between these two. And if you are making a decision on the null hypothesis, it means you are saying that there is no significant difference if you had a treatment or if you made an observational research. There was no significant difference in between the groups, okay? And then you have to make a research conclusion. Research conclusion is different than statistical conclusion. Research conclusion is about your research question and problem statement. You have to interpret the statistical significance in terms of practical significance. Is this statistical significance practical? Is it also practically significant? And what are the interpretations of that? The research conclusion is very important in a research study. Generally, we write the research conclusion in the conclusion part, and generally we leave it to the end when we write our thesis or reports. But it is the most significant part, because this is where you are actually presenting whatever you have done. Whatever you want to add to the literature is in this part. And in terms of statistical practice, the things that you can make are, you can build models, set clearly defined goals for the investigation with the research questions. You need to make data collection, make a plan of what data to collect and how to collect it, which is the research design. This is your research design, actually. If you have a survey study, it means you are going to send out surveys and collect them. If you are making a pre-test, post-test design, it means you are going to give a pre-test, make some kind of a intervention, and then you are going to do your post-test. So make a plan of what data collect and how to collect it, which is the research design. The data analysis is apply appropriate statistical methods to extract information from the data. And data interpretation is where you are actually now telling what you have found and how to interpret it. You can also make comparisons to the literature here. Interpret the information and draw conclusions. And conclusion and discussion part is this part actually. Okay, how do I describe numerical data if I'm doing a descriptive statistics? Or what should I use for describing data numerically? So I have a set of data. For example, the age of my students in a specific class, or the achievement test results in a test. How am I going to describe that numerical data? How can I understand it? Consider it like this. Somebody is coming to you and says, I got a 60 in the exam. I got a score of 60 in the exam. What would be your next question? He is trying to say his achievement level and comes to you and says, I have a score of 60 in the exam. What would be your next question to him, her? Exactly. You would ask, what is the mean? What is the average? Is 60 below average, or is 60 above average? Why is that important? Why is arithmetic mean important? To understand whether the success level, the achievement level of the student, to make an interpretation of the success level of the student according to the remaining scores. We can use arithmetic mean, but sometimes arithmetic mean by itself might not be enough. Because what if the arithmetic mean is 58 and everybody in the class had scores between 55 to 62, and there are 100 people, but all of them had the score of 55 to 60. What meaning does that have? It doesn't have any meaning because there is no variance. What we want in statistics is we want to look at the variance, okay? How the data is distributed. Where does it start? Where does it end? Where is the mean and where are the different scores divided and separated in the mean? So we can have central tendencies measures of arithmetic mean, median, mode, and geometric mean. I'm not going to go into the details of those. We can look at the variation. So what is the minimum score? What is the maximum score? The range, okay? What is the minimum? It would be different to interpret a score range of 50 to 65 than the minimum is 5, the maximum is 95. The range is totally different. These are totally different varied data sets. So we can look at the range. We can look at the variance, which is quite important. We can look at the interquartile range. But where exactly is our score? And how is it distributed in terms of probability to occur? Is it a very low probability that I get that kind of a score? Or is it a high probability that I would get that score? So for that, I need some kind of a value that shows how the data is varied in terms of percentile levels and probability levels. And I'm going to use a standard deviation for that. And I'm going to use coefficient of variation for that. And another thing, Did everybody get high? Did everybody get low? Or is this a normal distribution? Okay, if everybody got high, this doesn't make any meaning. I mean, it's all on the upper side. If everybody got low, this also doesn't make any meaning for me. It has a meaning, but of course, I wouldn't be able to understand the distribution. But so skewness of the data, if it's a normal distribution, that's when I can do some kind of work on it. So there are some tabular and graphical procedures that I can do with my data. In terms of qualitative data, I have two types of data. There can be two types of data. I can have the qualitative data and I can have the quantitative data. Qualitative data can be either nominal or ordinal data that I can collect, like the preference of car brands. Okay, the preference of color, the preference of drinks, or anything that's nominal or ordinal. How many of each you have? How, for example, the distribution of international students from different countries. You have qualitative data. For qualitative data, we can use the tabular methods like frequency distribution, this much of that, this much of this, and this much of that. We can have also relative frequency distributions, percentile frequency distribution, and cross-tabulation. In terms of graphical methods, we can use bar graphs or pie charts. Bar graphs, you might have seen them like histograms. They are showing the level of a certain amount or the frequency, and then you make comparison to the other ones. About the pie charts, when you have a distribution of different things that make a whole, when you sum them together, then you can show how much of the whole each represents. So, which one to use in which case? For example, if you are looking for, if you want to compare the sales of cars of different companies, which one would be better, the bar graph or the pie chart? Bar graph. Why bar graph? Thank you. That's a very good explanation. Bar graphs, because bar graphs are for comparison, making comparisons. Where do I use bar charts? If, for example, there is an election prediction and there are different parties, different people who are who want to be in the election. If you want to show as a whole the whole voters' choice, since it's a whole, you can show the percentiles or the numbers on a pie chart. But remember, for using the pie chart, you have to have a whole. You have to use 100% and show what part of that 100% represents a specific portion. In the quantitative data, we can use the tabular method, especially for descriptive analysis. We can use the frequency distribution, relative frequency distribution, cumulative frequency distribution, cumulative relative frequency distribution. Stem and leaf display cross-tabulation are all tabular methods for presenting descriptively quantitative data. And there are also graphical methods like dot plot, histogram, ogive, scatter diagram are all methods that you can use in terms of graphically and descriptively present data. So we can present data in two ways, my friends. We can present data, numeric data, in two ways. We can analyze them in two ways. One of them is a descriptive analysis. Descriptive analysis means anything like frequencies, percentiles, how much something has occurred, what is the mean, what is the standard deviation, and so on. Descriptive data can be just presented, and it gives an information to, it leaves the information and interpretation to the audience, okay? There is also inferential analysis. In inferential analysis, things change, because in inferential analysis, you have to conduct statistical tests. In inferential analysis, you are looking at a sample and try to make decision on the population. So you have 25 students in a specific place doing a specific thing, and then you want to interpret it for the population. That's inference, okay? And that's why we have inferential statistics, to go from the statistics to the population. Why should I go from sample to the population? Because in most cases, it will never be possible to work with the whole population. You have to select a representable sample that represents the population. So we will come back to this point, but first let's look at events and probability, because this is also the underlying idea of doing inferential statistics and mean comparisons. Why do we say statistically not significant? What's the reason? What makes us say that the mean difference is statistically not significant? Where do we come from to that decision? What's the reason that we come to that decision? There is an alpha value, but where does that alpha value come from? Where does the probability value come from? The probability value comes from events and probabilities. So performing the same random experiment repeatedly, you are doing the same experiment repeat again and again, may result in different outcomes. Do you think you will have the same mean again and again? You are giving an achievement test to your students, okay? And then you give it to another group of students. You give another group of students. Do you think they will all have the same mean? No. But they are from the same population. You taught them the same content. Why are their means different?
Probably mortality or maturity value is changing.
Mm-hmm. What if nothing has changed? Why? Because there are personal differences between the students, okay, within the groups, and you would never expect the same result. That's a natural outcome of sampling, because different samples will have most probably different means. But how different are those? There we go to the statistically significant or non-significant issue. If you there are different, but they are not statistically significant different. It's just because of a chance. Think about it like this. If we toss a coin, okay, everybody of us brings out a coin and tosses 10 times. We toss it 10 times. The probability that some of us have 5 tails and 5 heads will be more than some of us having 10 tails or 10 heads, okay? So if you would put them into a distribution, the number of us who have 5 tails and 5 heads would be much more than those who have a little bit different, and those who have totally no tails, no heads. So the probability of occurrence of a certain outcome, that's what we can actually consider. We cannot be sure. We cannot say from the beginning, there will be nobody who has 10 tails. We can't say that. Because all events are mutually exclusive, meaning one is not affecting the other. But still, we can say there will be just a few persons, if any, who will have all tails or all heads. So to determine the probabilities, we need to define and list the possible outcomes first. What are the possible outcomes? And that's the sample space, my friends. We call it the sample space. Determining the outcomes, build an exhaustive list of possible outcomes, make sure the listed outcomes are mutually exclusive. By mutually exclusive, I mean one of us having 6 heads, 4 tails is not affecting another having 7 tails and 3 heads. Is not affected from each other. They are mutually exclusive. The set of possible outcomes of an experiment is called a sample space and denoted by S. For example, tossing a coin experiment, the S, either it can be head or it can be tail. Rolling a dice experiment, it can be any one of these 6. Determination of the sex of a newborn child, it's either a girl or a boy, okay? So the sample space is equal to the possible outcomes of an experiment. The outcomes must be mutually exclusive and exhaustive, meaning there should be a range of possible outcomes. In the case of tossing a coin, it goes from no heads at all to all heads, or no tails at all to all tails. Okay, so the sample space is limited. The possibilities of outcomes are limited. And the individual outcomes are called simple events. So these are all simple events. And an event is any collection of one or more simple events. So this is what happens really when we do it. When we actually do it, this is the event that occurs. And it will include some simple events. Okay. So given a sample space of S is equal to events 1 to K, the total probability of all the events to occur is 1. It cannot be more than 1, okay? It is going to be equal to 1. So all the probabilities of happening should be 1. And probability of an event, probability A of an event is the sum of the probabilities assigned to the simple events contained in A. When we are going to build a contingency cross-tabulation table, we are putting the counts of 2 or more variables in a comparison, okay? So the event of A1, A2, the event of B1, B2, and then we are giving it like this. Why is this important? Because cross-tabulation is very important for descriptive analysis. In descriptive analysis, when you make comparisons, you are comparing the different events and how they can occur together and how they can occur separately. And this is why we have to give them as separate rows and columns and give the possible numbers that they can occur together and separately in the rows and columns. In terms of joint probability, the joint probability is the probability that two events will occur simultaneously, okay? Two events will occur simultaneously. And marginal probability is the probability of the occurrence of a single event. So like this. The joint probability would be B1 and B2 in the case of A1. So marginal probability is only the occurrence of a single event. And altogether, they need to go up to 1, the probability value. So that's the joint probability A2 and B1. And that's the marginal probability of A1. Now, if you go into the statistical tests, the type of statistical test, parametric tests. Everybody here in the room, did you take a statistics course? Anybody who did not take a statistics course here? You did not take a statistics course, so this might be kind of a little bit on the air, but still try to, if you have questions, just ask it. But if you have taken the statistics course, this should be something that reminds you to those things during your statistics. So let me remind you about the statistical tests. We have the parametric tests, okay? What does parametric mean? What is a parameter? What is it? It's a measurement, but measurement of what? Parameter. Parameter is the measurement of something in the population. So it's the value of the population. Please write it down somewhere in your head or somewhere. So parameter is the value, is the data value measurement of the population, of the whole population, okay? Parameter, the whole population, the average age of the population in a specific region, the whole population, okay? Statistics is the measure of a value of the sample, okay? So if we are talking about the sample, we are talking about the statistics. If we are talking about the population, we are talking about the parameter. Okay. Now, when we say parametric tests, we mean tests that are related to the population measures. Okay, tests that are related to the population measures. So based on assumption that the data have certain characteristics or parameters, results are only valid in the parametric tests. Results are only valid if the data are normally distributed, okay? But here I have to say something. Don't expect perfect normality. There is nothing like a perfect normality. A little bit skewness is okay. There are skewness tests. You can use them, whether they are acceptable in the skewness level. But approximately normal is okay. approximately normal is okay. You don't need perfect normal. The data show homogeneity of variance. What is homogeneity of variance? What is homogeneity of variance? You have a variance. Variance means how the data is distributed, okay? But the scores start from 50 and go up to 60. There is a hard going up, hard going down, so a bumpy distribution. And then you have another sample which has like the minimum is 5, the maximum is 95, very smooth. Are the variances homogeneous? No, they are not, because one is bumpy and high, the other is smooth and like a normal distribution. So homogeneity of variance, if you make sample comparisons, you cannot compare apples with oranges, okay? Apple is a different thing, orange is a different thing. You cannot say apple is whiter inside than orange. We don't expect orange to be white. So the nature is different. So if you want to compare means, they should be comparable in terms of the type of data, in terms of what you are comparing to each other, and in terms of homogeneity of variance, how they vary. And the data are measurements on an interval of or ratio scale. If you want to do statistical parametric tests, you have to have interval or ratio scale. If you are going to use non-parametric tests, you don't need to make any assumption, okay? Because you are not going to infer, you're not going to infer what you have found in the sample to the population. You are just going to interpret it in terms of, whatever you have. These and this group were different. You will not say the population from where this group is coming is different from the population where this group is coming. You will only say, you need to only say, these two groups are different. This is a general mistake that generally are done by graduate students. Overgeneralization of the results. Maybe working with just people of 25 and generalizing that to the whole population in the country. How come? That might not be a representative of the whole population. You can't do that. Okay, so non-parametric test. If you are using a non-parametric test, you can't do any type of generalization, okay? Do not make any generalization in the results interpretation. Just say this one and this one was different. I used to have implement this one in that group, and I used to implement this one in the other group, and they became different. They came out to be different. That's what you need to say, nothing else. If you are doing a case study or something, it's okay. Yeah, you can only interpret those groups or that group.
So you just want to use EduTech class.
You are using it because you might have done a convenient sampling, because that's the group that you can only work with, and you don't have a normal distribution, but you still want to compare it to another group. Interclass, yes.
Interclass. use the whole population.
Oh no, if you are doing the whole population, then you can of course make the parametric test if it's normally distributed. If it's not normally distributed, you can still not do the parametric tests. So if the data are not normally distributed, negative skew or positive skew, the data show inhomogeneity of variance, the data are measured in ordinal scale, then you cannot use parametric tests, but you have to switch to non-parametric. Parametric tests always are stronger than non-parametric tests. So
in the parametric state, you said it is normal.
for the parameters, you have to have approximately
It's nominal and use nominal and interval.
no ratio and interval.
Ratio and interval.
Yes,
Here you use
nominal or ordinal. Oh, and you can of course use ratio and interval as well here, but the distribution should be skewed, non-normal, not approximately normal distribution. Okay, and the distribution can be small. If you can't collect that many, if you have only 12 students, it wouldn't be quite meaningful to do parametric tests because you have a very small group of students. Even t-tests might be not very reliable. You have to switch into non-parametric versions of the test. Doesn't that make meaning? Because with 12 people, you are trying to infer, generalize it to the whole population. This would be something like this. I'm from Turkey, and you know only me, and you say, the Turkish people all wear ties. Why? Because I saw one Turk, he was wearing a tie. Everybody is wearing a tie. Okay? Nonsense. You can't just look to a small group and then make interpretation for the whole population. But if you would have seen 25 Turkish people coming here or somewhere else, you would say, no, I have seen just one or two professors who were going around wearing ties. They don't wear ties every day. Would be a much better interpretation based on the data. So if you have only 12, it's too small to make any interpretation. That's why you can't use parametric tests. You have to switch into the non-parametric test. You can say this. That specific person wears ties, and another one does not. That's only what you can say. In terms of parametric tests, the Pearson correlation, if you are looking at relationships of something, if something is going up, is another thing also going up? Are they moving together? Or if something goes up, does the other thing go down? Two variables. If you have enough data and if they are normally distributed, you can do the Pearson correlation. If not, you have to do the Spearman's correlation. That's the non-parametric counterpart of it. And if you are comparing several things, like a matrix of things together, you can use chi-square test. If you are comparing means to each other, you can use means from different samples. You can use the independent means t-test. The counter version of the independent means t-test, if you do not have enough size, if the data is not normal, is Mann-Whitney test. if you measure two separate things of a sample, of the same sample, and compare them, like the achievement in math and the achievement in science classes, okay? You compare those for the same group. This is dependent means t-test, and Wilcoxon signed rank test is going to be used if you want to have a non-parametric counterpart. One-way independent measures analysis of variance if you have more than 2 variables. If you are looking for 3 variables, motivation, achievement, and self-regulation, you have 3 variables. And then you want to make some mean comparisons. Then you use ANOVA, and the counterpart is Kruskal-Wallis test. The list of all tests that you can conduct, the test list is chi-square, Spearman correlation, Pearson correlation, independent sample t-test, dependent sample t-test, one-way ANOVA, two-way ANOVA, ANCOVA, MANOVA, Benforoni test, Sheffield's test, Mann-Whitney-Ure test, Wilcoxon signed rank test, Kruskal-Wallis, and Friedman analysis of variance. Now you are, I don't know in which stage of your research you are. You are going to collect data and make some type of data analysis. Do you know which one you are going to use? Most probably not yet. Most of you, most probably does not know which of these analysis is required for his or her data analysis phase. But don't worry, because I'm going to tell how you can find it. You're welcome. So let's first understand what each test is, okay? What are those tests? In terms of chi-square, sometimes we also call it chi-square. I like chi-square better because it reminds me about chai, which is tea in Turkish. Chi-square, and we have 2 types of tests here, the goodness of fit and the test of independence. And it's a non-parametric test. It is for statistical tests of association. The data must be discrete and at nominal or ordinal levels. And the frequency data are arranged in tables to compare the observed distribution, your data, with the expected distributions, what you would expect to find if no difference existed among the values of a given variable or variables. Let's find an example for that. You have the polls about an election, okay? And then you have the results of the election. If you compare these two, that's the chi-square goodness of fit. Whether one was able to interpret it, the result, in a statistically acceptable way, whether the predicted results and the actual results fit into each other, you can do the goodness of fit, okay? In terms of correlation, we have the Pearson correlation, which is parametric. Now, what does parametric mean? It can be inferred to the population, okay? Inference is possible. Can be inferred to the population. If the data are interval normally distributed, the basic test for linear straight line relationships is the parametric Pearson product moment correlation technique. The correlation results for Pearson correlation can fall between +1 and -1. If it's +1, they means the two variables are positively correlated. While one is increasing, the other one is increasing too. Can you think about an example? When one is increasing, the other one is increasing too. The time for studying on the test result. While one is increasing, the other one is also increasing. They are positively related to each other. They are not perfectly correlated. It doesn't mean if you study 2 hours, you will get that score. It's not possible, but still, they are predicted. They are correlated. So one is increasing, the other one is increasing too. Can you think about negatively correlated? When one is increasing, the other one is decreasing.
Not the negative.
Yes, they are really correlated, but it's negatively correlated in different directions. One is increasing, the other one goes down.
That is the -1.
Yes.
When you said the +1 is when they are going.
When they go down together. It means still positively related. The negative means one is going up, the other one is going down. Can you think about something? The time, okay. The level of income and leisure time. The time for leisure, for relaxing. The total income of a person, the time for leisureness might be negatively. So if leisure time goes up, if leisure time goes up, do I make the no? Then the working time maybe. That could be, yeah. Or a better example. Let's think about a better example. Age and strength, yes. When the age goes up, the physical strength after some age goes down. If you are above the middle age, then it goes down. So anything above R.4 or below R.-4 might be considered a moderate relationship between two variables. If you can't make Pearson correlation, the next choice will be Spearman correlation. If the sample is small, or if the data are ordinal, rank order data, then the most appropriate choice is the non-parametric Spearman rank order correlation statistic. The correlation results for Spearman correlation can fall between +1 and -1, just like Pearson correlation, and anything above R.4 or below R.-4 might be considered a moderate relationship between two variables. Okay. Income and spending as increases, the other increases. Okay. No, it means they are totally unrelated. If you have a correlation of 0.00, it means they are totally unrelated. If it goes to plus or -1, it means they are strongly related to each other. And it depends whether they are negatively or positively related by the sign of the result. So independent t-test. This is one of the most frequently used if you want to compare two means from two different samples, then you are using independent sample t-test. That's why it's also called two-sample t-test. Is used to test the difference between the means of the two groups. It's parametric. So if you are doing an experimental study, which has only one variable for two groups, if you are only comparing their achievement level, this is the test that you need to conduct, okay? Also called the two-sample t-test, is used to test the difference between the means of the two groups. The results of the analysis is reported as a t-value. It is important to remember that the two groups are mutually exclusive and not related to each other. Sometimes we oversee this. Like we have two classes that we teach, okay? For one, we are implementing something. For the other one, we implement something else. And then we look at the achievement scores, but we don't take into account that there can be some kind of a peer teaching to each other, and that they could be sharing your whatever you do in the one with the other. So there is a confounding variable actually there that you don't take into account that affect your result.
What of this? For example, we are using S-color printer, and the two groups are located in different districts. One in Johor, probably one in Colorado, and they are both students. So is there any interaction?
Can be online. You know, it depends on your design. If you are sharing a specific, if you have created a different types of material for one and another type of material to the other, and you want to see if that material makes a difference, you have to make sure that the second group does not have any access to the material. There can be communication between these two, but they should not be able to have access to the material.
They are all controlled.
Yeah, they should be. They should be separated from each other. There shouldn't be any confounding variable.
No, my argument.
I couldn't get that. Sorry. What do you?
Means they are all controlled. No one that is going to have this balance. One here and one in Johor, and they are sharing the same data.
No, there are two different groups. One is the control group, the other one is the experimental group. It depends on how you design your experiment. If you apply something new to one, that's the experimental group, because then you are doing the experiment on them. The ones that you are still continue to as you were doing it before is generally the control group. But in education, we don't prefer the term control group, because no group can be a control group of another one, because you are doing something else there too, okay? In medicine, it's possible. I'm giving you some pills and I'm giving the other ones no pills, or I'm giving pill-like things so that they think that they are getting the pill, that the medicine. So that's the control group, because I don't do anything different to them. They don't get treated at all, while one group gets treated. That's why we prefer the term comparison group, okay, rather than the control group. In educational research, we prefer the term comparison group. We are comparing it to that one. It's not the control, it's the comparison group. It doesn't matter what they use. The meaning is, even though that you are doing the same thing to them as you were doing before, but still you are doing something, I mean, which might be different from someone else doing something. That's why they are not the control, they are not the baseline. Control would mean baseline, but they are not the baseline. Okay, there is a question here. Is it possible to correlation is SI 0.99? In normal cases, not. We wouldn't expect, because if you would have a if you would have a 1 as a correlation coefficient, it would mean perfect correlation, which would mean a machine or a formula relation, okay? Which is not quite common in human research, in behavioral research. In behavioral research, we don't expect that amount of correlation. Okay. So the result of the analysis is reported as a t-value, and it is important to remember that the two groups are mutually exclusive and not related to each other. That's what he said. Dependent t-test means, also called the matched pairs t-test, is used to show how a group differs during 2 points in time. For example, if you are looking for the within change in the group before and after the treatment, okay? The matched t-test is used if the two samples are related. This test is used if the same group was tested twice, or when the two separate groups are matched on the same variable. Okay? Why? Because in educational research, when you do a experimental study, let's say you are trying a new treatment, you are trying to implement a technology enhanced instructional approach to one group, while you are doing a traditional instruction to the other one, okay? And you want to compare the achievement scores. If for your control group, you do still something, okay? You are still doing something with them. While for the experimental group, you do something different. If the thing that you are doing with this control group, if you would change the teacher or any other circumstance, could there be a change? Could there be a difference?
It is what he is trying to see if there is any difference.
No, I mean the control group, for the control group. If you would change the instructor or any other circumstance, could that cause a change in the control group?
Yeah.
So it's not the baseline measure then. Because it can change according to different variables, other different variables. So that's why we don't call it the control group. Control group would be something baseline, okay? If you don't take the drug at all, that's baseline. If you don't take a medicine at all, that's the baseline. But if you take a different version of a medicine, that's not the baseline. You are still taking some form of a medicine. And that's why it's more proper to say comparison group rather than the control group. Could I make it clear? Okay. And then we have the one-way ANOVA. Analysis of variance is used to determine differences among means when there are more than two groups examined. It is the same concept as the independent t-test, except you have more than two groups. And if there is only one independent variable, usually nominal or ordinal level data, consisting of more than two values, then the procedure is called a one-way ANOVA. Then we have the two-way ANOVA. If there are two independent variables, you would use a two-way ANOVA. Okay. We have ANCOVA in case you have a covariate. What is a covariate? let's clarify what the covariate is. Would you think that the previous skills, the previous knowledge of students could affect the final achievement test after a specific treatment? For example, their existing skills in math, could that affect the achievement scores in the math course in the end of the year? Could it affect? It is possible. Yeah, we have. So if it is possible, we have to take it into account. And to take it into account, we are actually, since they are covariate, they are variate together, while the previous skills are increasing, the achievement score also increases. We have to put it as a covariate. Generally, previous knowledge or something else that might in the literature shown as affecting the result can be used as a covariate. Okay? MANOVA is a kind of a more complex analysis. So multivariate analysis of variance or multiple analysis of variance is a statistical test procedure for comparing multivariate population means of several groups. So if you have even several groups, then you want to compare the variables, then you have to switch into MANOVA. Then we have the Banforoni or Sheffield's test. ANOVA, if you are using ANOVA, it means you have 3 or more variables, okay? The ANOVA test will tell you if at least one of the means is different, but it will not tell you which ones are different, okay? The ANOVA test will say, if you have 4 variables, the ANOVA test will say at least one of them is different. But it can be two of them might be different, 3 of them might be different from each other. You have to use this Banforoni or Sheffield's test as a post-test to find out which ones are different from each other. It's called a post hoc test. Okay, then we have the Mann-Whitney U test and Wilkinson-Saint-Ranks test. They are both non-parametric. The Mann-Whitney U test is used to test for difference in ranking on some variable between the 2 independent groups when the data are not scaled in intervals. This test is equivalent to the parametric independent t-test. Okay, parametric independent. So independent t-test, if you can't use it because of skewness, because of small group, okay, then you have to switch into Mann-Whitney U. The Wilkinson-Saint-Ranks test is a non-parametric alternative to the t-test and is used when dependent variable has more than 2 values that are ranked. So this is just like dependent sample t-test. Then we have the Kruskal-Wallis. This test is equivalent to the one-way ANOVA. You have 3 or more variables, but they are not homogeneous, they are not normal, or the number of people, the number of sample size is not enough to go for parametric. You have to use the non-parametric. You can still compare them, but you need to have the non-parametric Kruskal-Wallis. Friedman analysis of variance is used instead of two-way ANOVA. It's a non-parametric version of the two-way ANOVA analysis. Here is a comparison table, okay? If you have a single sample, to determine if an association exists between two nominal variables, you need to use the chi-square. Two samples between subjects. So two separate samples between subjects, not in the same group. To determine if the populations of two independent samples have the same means or median, the parametric is the independent t-test, the non-parametric is the man with METU test. If you have two conditions within subjects to determine if the populations of two samples have the same mean or median, then dependent t-test or sign test or Wilkerson sign rank test. More than two conditions, more than two variables between subjects to determine if the populations of more than two independent samples have the same mean or median. One-way ANOVA, non-parametric is Kruskal-Wallis. More than two conditions within subjects to determine if the populations or more than two samples have the same mean or median. Repeated measures ANOVA for the parametric, and for the non-parametric we have the Friedman analysis of variance, and set of items with two measures on each item to determine if the two measures are associated, the Pearson correlation or the non-parametric Spearman. Let me tell you something. When one of the parametric tests finds no significant results, so will the counterpart non-parametric. So the result will not change. Okay? Just keep in mind. It will not change the result whether you are using non-parametric or parametric tests. If the result is non-significant, it will still be non-significant, whatever you use.
What if it's significant, right?
If it's significant, it will be significant. In the counterpart. Okay, here is an algorithm for you. The first thing that you need to ask yourself, is the dependent variable ordinal, interval, or ratio? Okay. You know what kind of data you have collected, so you can decide whether this is ordinal, interval, or ratio. If the answer is yes, the next question is, are you comparing a sample mean to a known or hypothesized population mean? If the answer is no, is the dependent variable measured more than once? If the independent variable is measured more than once, are the dependent variables ranks related to one another or from the same case? If not, you need to stop here. If yes, is the dependent variable measured more than twice? And according to the answer, if yes, you need to choose Friedman non-parametric analysis of variance. Is there more than one independent variable? If yes, you can choose the two-way chi-square or choose the one-way chi-square if not. So are you comparing a sample mean to a known or hypothesized population mean? Do you know the population standard deviation? If yes, choose the one sample z-test. If not, choose the one sample t-test. Now we are going down. Are you comparing sample mean to a known or hypothesized population? And the answer was no. Okay? So the answer was no. Are you comparing the means of two samples? If you say yes, are these two samples related? If they are related, dependent t-test. If not, independent t-test. If no, if you are not comparing the means of two samples, are you comparing the means of more than two groups? Is there only a single independent variable? Then you have to choose ANOVA. If not, if there are more categorical independent variables, choose the two-way ANOVA, if yes. If not, you cannot continue the analysis. Okay?
Stop there.
You stop there because you have to go back because there is no way, any other options. Are you interested in describing the relationship between the two variables? If yes, are the variables interval or ordinal? If so, you can use the Pearson correlation. If not, choose the Spearman rank correlation. So this is the algorithm that you might use for selecting the correct type of test for your data. There's a question in the chat. Let me. Meaning if my sample number is small, I still can analyze using Pearson. I could get your question, Renee. Could you be?
So, hi, doctor. I'm Renee here. Meaning that if my sample number is supposed to be non-parametric, right? Because my sample is small.
Give me a number.
Like 18.
18.
Yeah.
18 is just in the middle. I mean, there is no agreed number, but generally statisticians agree on number 25 to be
yes.
To be able to use parametric tests.
Yeah,
okay?
but I didn't get 25. I only get 18.
18.
Yeah.
Then you have to look at your at the nature of your data. You can decide to continue it. It's not a written rule. It's not a law. Okay. This is just an analysis that you use to interpret your result. So if look at your data, if your data not have too many outliers, if there are outliers, some of them are like in different places in your scatter plot, it means there have been something that was not reliable. Maybe some of them did not answer honestly. Some of them just encircled one without reading. If you encounter such things, you need to exclude those. If you don't have such things, you can still continue with, and if you look at find an approximate normal distribution, you could still continue with Pearson correlation.
My limitation is, doctor, my sample is among expatriates in Johor Bahru. So expatriates, because they are very busy, even I give them, they are very busy, and I must have a very, have a close encounter with them. So I will keep reminding, can you please spend your time, 5 minutes to answer my questions? So I done that and I only get 18. From my target is 30, but I cannot get 30. I only get, so they are very busy, and I mean the numbers of expatriates in Johor is about just 1,000 something. It's not that big.
Okay. Yeah, that happens in behavioral research. The hardest place to work is the field. When you actually have to collect the data, you will face the reality, and when you face the people who you want to collect the data from, they won't be very happy about sharing data with you. So it has always some difficulty to collect reliable data. But Renee, if you think that your data is unreliable, I wouldn't go any further, and I would try to find another way of collecting data. You have to be, because you cannot have reliable results based on biased data. Okay, the data itself should be reliable so you can have reliable results. So make sure that your data is reliable.
Based on my,
They
based
might
on my,
have put 5 minutes, but still they might have provide you with the correct, with their correct opinions or whatever you are asking for.
based on my supervisor, she
Mhm.
said my sample actually is reliable, so that's why I continue.
Okay.
Yeah, but just like, because just now when doctor said that, if non-parametric better using Spearman, and if parametric use as a person.
Yes.
So which one is better for me, doctor?
If I were you, I would go for the Spearman.
Oh, okay.
The resulting correlation won't be much different. The resulting coefficient value isn't going to be much different. If Pearson shows a high correlation, Spearman will also show high correlation.
Okay.
Okay?
Okay, all right. I understand.
Why don't you try both and then talk with your supervisor about the results?
Yeah, I plan doing that. I want to do both.
Yeah, please do both because it's
Yeah, I would
just a
do
matter
both.
of clicking a few buttons just
Yeah.
in SPSS and then you can just compare the results.
Yeah, I want to do that.
Okay, good luck with that.
Thank you.
Okay,
Thank you.
Matrix correlation.
which one?
Matrix correlation.
Matrix?
Matrix.
Matrix for correlation? What kind of matrix are you looking for?
No, I'm asking on the matrix correlation.
Okay. I didn't get that. I couldn't get that. Maybe we can talk later on. So I could. Okay. I would like to thank you everybody online and here in the class for joining the session. I hope it was kind of helpful to understand at least what you are doing in terms of parametric, non-parametric tests in educational research. And I wish you a nice day. Take care. Bye-bye.
Thank you very much for all.
Thank you.
So I hope that you will get benefit from the talk that I will be and maybe if there's like any further questions in the future, you can
Sure.
send email.
Yeah.
Okay, so thank you, Prof. Ömer again, and